So welcome everyone. We've got an awesome program, and because today is the day that's more focused on issues around it from qubit, quantum information, and our first speaker, and I'm super excited to hear from her, is Netta Engelhardt, who is at MIT, and she's going to tell us about free energy from Replica Wormholes.
Thank you very much, Scott. And I want to thank all the organizers for persevering and putting together this workshop, not allowing 2020 to take the annual It from Qubit meeting away from us. So thank you for that. The program really does look exciting, and I'm not only talking about my own talk. So thank you. And yeah, let me begin. So this talk, as you can probably tell from the title, is focused on replica wormholes. But it's not going to be focused on the replica wormholes that we normally see or have been talking about in terms of the entropy replica trick, but rather a different quantity. I'm going to talk about replica wormholes that contributes to the calculation of the free energy. And this is based on a paper that came out last July with Sebastian Fischetti and Alex Maloney. So let me begin with sorry, just one second, my computer froze for a moment. Okay, let me begin with just a little bit of motivation here. So given that we've spent a long time looking to calculate the unitary page curve, it's been an arduous few decades. And of course, the recent developments have given us one way of computing a unitary page curve. So that's been very exciting, but I think it's really important to understand in broad generality what the microscopic explanation is for the success of the quantum extremal surface formula in explaining in reproducing a unitary page curve. So when I say microscopic, I really mean coming from quantum gravity. So that, of course, is a very difficult task. But as a starting point, we have the instructions from the Lefkowitz multisigma procedure, which tells us how to go about computing this or justifying this from the gravitational path integral. And of course, the contribution of replica wormholes has raised new questions about old insights on Euclidean wormholes and, of course, ensembles in gravity. Now, again, this is just a review of what I think most of you have seen maybe ad nauseum at this point in various conferences. So what are we doing in this talk that's maybe a little bit different? So what we're doing here is we're asking, with a view towards understanding better why these replica wormholes are permitted to contribute, what it means that they're contributing, whether they actually leave a footprint on other observables. And we're really looking at the generating functional and the free energy, because there's a sense in which it is more primitive, but also because it can also be computed via a replica trick. And computing it via replica trick versus not computing it via replica trick gives two different answers. So it's rather reminiscent behavior of what we've seen with the von Neumann entropy. So let me begin with the actual talk. So I'm going to first introduce a little bit of notation with things that I think everyone here is familiar with as far as the von Neumann entropy replica trick, just to really establish some notation. And then I'll talk about this replica trick that I advertised for the free energy, which is not something new. And in fact, I believe it's older than the von Neumann entropy replica trick. And after that, I will move on to free energy in JTT Gravity. We would have loved to compute the free energy from this replica trick in general theories of gravity, but now, working in Euclidean signature, you can rewrite the state in terms of the Euclidean partition function, which ends up being rewritten in this way. And again, I think everyone has seen this before. Here, Z of B is the partition function on the space B. So for us, that will be the boundary. And Z of B sub n is the partition function on B sub n, which is an n-sheeted geometry that consists of n copies of B that are cut along R and then cyclically identified along R. Now, one thing that we often do in ADS-CFT, we'll just replace the partition function with the Euclidean path integral. And so Z of B is replaced by the Euclidean gravitational path integral with boundary conditions B and z of b sub n is replaced by the gravitational path integral with boundary conditions b sub n. Now, if this allows you, if you want to do, say, a perturbative analysis around n equals 1, this gives you the Ryutaki-Yanagi formula via Lefkowitz-Maldacena. And in the, for example, East and West Coast papers, this type of technique also gives you the quantum extremal surface formula. Now, what we also all know is that in order to correctly reproduce the unitary entropy result in this way, the gravitational path integral receives contributions from connected topologies, the so-called replica wormholes. Now, this, of course, leads to something that has garnered a lot of discussion recently, which is the issue of non-factorization due to the inclusion of connected topologies. So if we literally take the gravitational path integral to be computing a partition function, then we find that the partition function, we have a factorization problem. So one possibility that has long been discussed in the literature is that the gravitational path integral actually computes an ensemble average. Now, so P of B is Z, what we call overbar, so this is the average. I'm actually going to use overbar here to denote whatever it is the gravitational path integral is computing. And another possibility for what that is that it's just removing, it's course graining over some non-perturbative corrections, which restore factorization. A third possibility is that it's just a really good tool for computing quantities that are self-averaging in a single chaotic theory. Now, I am not going to be subscribing to any one of these in particular today. I'll be completely agnostic about this. I am going to use this overbar just to denote whatever it is the gravitational path integral is computing. Of the three yet, so I'm going to remain agnostic about which one it is. So a few questions. If the gravitational path integral is averaging, what is it averaging over? If it's not averaging, what is it calculating? What are the implications of this on other observables? And of course, the main point of this talk, we could ask if we see this in the generating functional or the free energy, the fact that the gravitational path integral is allowed to receive contributions from these Euclidean wormholes. So this finally leads me to the main point of this talk, so enough with the introduction. So if the gravitational path integral receives contributions from connected topologies, then in principle, it's not impossible that if we compute log of z bar, again, this is the log of just the gravitational path integral, or if we compute this quantity, which is, we say, directly computed from the gravitational path integral, if it's an ensemble average, the log of z, the ensemble average of log z, there could be a significant difference between the two. So, for example, in condensed matter systems, these two have two different names. They're very well studied. This first one is called the annealed free energy, which computes an average over random variables that define a particular instance of the ensemble. So this is in the case where you actually are doing an ensemble average. And that suggests that log z bar here is really more like a generating functional in a theory where the random variables are allowed to equilibrate. Now, the second one, the so-called quenched free energy, or the quenched average, computes an average over the free energies of the constituents of the ensemble. So where the random variables are not allowed to equilibrate. And even if the gravitational path integral is doing something different, this latter one certainly has more of the flavor of what we care about in this case. Now, if it is true that the gravitational path integral computation of z of b to the n is not the same as the gravitational path integral of z of b raised to the power n, which of course would be the case whenever we have replica wormholes, then we might also expect that these two quantities, the quenched and annealed free energies, are also not equal. And so it becomes important for us to be able to compute both from the gravitational path integral and understand
Okay. Uh,
I guess it looks like Netta got disconnected.
yeah. Okay. Well,
We'll perhaps wait a little bit to get connected.
Back.
oh,
Yeah,
hi.
I'm back. Sorry
Okay,
about that.
okay.
Yeah.
Yeah,
All right,
we're having some connection problems. Sometimes your voice.
Oh, really? Okay. Let me try a different. Okay, is this better right now? This is I want a different network right now.
I mean, right now we hear you, but we
It's
can
in and
tell
out.
you if it happens.
You could turn
again.
off your video.
Yeah.
Okay, let me do that.
Okay.
That's great. But I will share screen share.
Yeah.
Okay.
We'll also turn off our videos in case. That's
Oh, let's see. Do you need screen sharing again?
I think I'm okay to do that.
All right, good. I mean, you are co-host.
Yeah. So sorry.
All right, there we go. Good.
Okay. Yeah. Sorry about that. Okay. So you'll notice this is a different replica trick. I'm not sure where I got cut off, but I'm going to start here. You'll notice this is a different replica trick. Here we have to take a limit as the replica parameter m goes to 0 as opposed to 1. So this is a different replica trick, but nonetheless, it involves the introduction of m replicas and then taking the limit as they approach a certain value. And so this is something that we can compute from the gravitational path integral. So we replace this by PB to the m, which allows us to compute this gravitational path integral average or whatever it's computing of log z of b. So just a comparison between the annealed and quenched free energies here. So if replica wormholes can actually contribute non-trivially in the m goes to 0 limit, then this is very different from the annealed free energy. The quenched free energy and the annealed free energies are going to be very different. So in the annealed case, we are only going to get contributions from disconnected topologies. And in the quenched free energy, because again, this is just one boundary here, but in the quenched free energy case, we actually can get contributions from connected topologies and replica wormholes. With your replica wormholes here. So this is an example where we have something connecting two boundaries. Of course, the real question is what can actually dominate in the m goes to 0 limit, whether replica wormholes can contribute in the m goes to 0 limit. Now, to ground this a little bit in something that's more familiar, let me just show an example of how to compute the von Neumann entropy in a holographic theory that actually involves doing 2 replica tricks rather than just 1. So here, again, we're doing the overbar. This means we're computing the von Neumann entropy using the gravitational path integral. So we do the same thing we did before, which is.
Netta, there's a quick question.
Oh, there's a question.
Could you define P of B? Daniel Harlow is asking.
Oh, sorry. Yeah, let me go back up. So P of B is the gravitation. That's I'm just going to say it since I think Alex answered it, but let me just say. So P of B, it's the gravitational path integral with boundary B. Boundary conditions.
All right, awesome. Thanks.
Yeah. So the average. So here we are computing the von Neumann entropy of a density matrix rho sub r as computed from the gravitational path integral. So really, what we should be doing, even though before we just had log zb sub n and a log z of b, really, if we have an overbar here, we should have an overbar over each of these. So actually, what we should be doing is a compounded replica trick, one for the von Neumann entropy and another one for log z, which means that really we are working with a much more complicated replica manifold, b sub n to the m, which is what I've attempted to illustrate here. So b sub n is going to be the same one as before, which was this n-sheeted geometry with this cut along R that's cyclically identified. And we also end up having m copies of these, which is what comes in for the log z replica trick. So this is so there's really a compounded replica trick when we're computing this from the gravitational path integral. Oh, sorry. So just as an example of one place where this could actually matter, so suppose we want to compute the von Neumann entropy for a pure state, which of course should be identically 0. If we don't use the log z replica trick, then we plug everything in here. And of course, we find that if replica wormholes contribute at any order, then terms will not cancel between these two, and it's not going to vanish identically for a pure state. It'll vanish up to whatever order the replica wormholes are contributing at, even though a pure state should really have vanishing entropy to all orders. Now, if we do use the log z replica trick, and for a pure state, we have b sub n to the m equals bnm. So we can rewrite it this way. We define m tilde here as nm. And plugging this back into this formula, we actually just get that this thing is identically 0, regardless of whether we get replica wormholes contributing at any subleading order. So this is nice. It shows us that this is something that we want to include. But of course, at the end of the day, this is not the kind of dramatic signature that we're looking for. We're really interested in something that's a more leading order. So let's get a little bit more into this log Z replica trick. If we're just working with log Z and we don't care about the von Neumann entropies, then we don't need this very complicated replica manifold geometry. We just need the M replicas just for log Z. And if we're working with ADS, we really are just going to have the M replicated ADS boundary conditions. So the question that Alex and Sebastian and I were asking is whether there is a simple theory of gravity with a regime where replica wormholes can actually contribute to log Z at least as much as the disconnected topologies. So we've already seen that they can contribute in the sense that it's important to include this additional replica trick if you want to get an actual 0 entropy for a pure state. But again, it's a subleading order correction. And the question we want to ask is whether there's something that can actually contribute at the point where it makes a big difference to the value of log Z. And that brings me to our calculation of the free energy in JT Gravity. So I know that some people thrive on calculations and some people really prefer not to see any calculations. So here is the big picture where I'm just going to summarize what we did. And then I will afterwards discuss in more detail what the technical details are. So this is mainly for those of us who prefer to just see the punchline without going through all of the details. So what do we find? We work in pure JT, and we do find that replica wormholes give a larger contribution to log Z than disconnected topologies in a certain low temperature regime. In fact, the disconnected topologies, if you didn't know anything about the replica trick and you just naively computed the annealed free energy, and you only included the disconnected topologies because that's what goes into the free energy, then that results in a pathological free energy. So it's clear that's not the full story. And when I say pathological, I mean that it's non-monotonic with temperature, which gives you a negative entropy. So that is already very problematic. Now, it turns out that if you do include replica wormholes, then even though the pathological behavior, at least prima facie, is mitigated by this inclusion of replica wormholes, it's not obvious that the inclusion of replica wormholes is actually sufficient. So we can't show that we don't actually find a monotonic free energy. What ends up happening is that we can only compute a partial inclusion of replica wormholes, including a resummation of the genus. I'll say more about that in a minute. But with this partial inclusion, even though the free energy is not as badly non-monotonic in some sense, it still is non-monotonic with temperature, and that's just bad. So we can ask, well, it's bad with disconnected topologies only. It's bad also if you include replica wormholes, at least partially. So what's going on? I mean, one possibility is certainly that this partial inclusion of replica wormholes is not enough, and if you include everything, then it works out. But one interesting thing that can go wrong is the analytic continuation as M goes to 0. It turns out there's a lot of freedom in how to do this. And the obvious or simple analytic continuations that you might think to do are just wrong. So it appears that there's a lot of subtleties in the analytic continuation itself. Now, this has some very intriguing parallels to replica symmetry breaking in spin glass systems, where you have a similar phenomenon that happens. If you just look at the annealed free energy, it's pathological, it's severely pathological. If you add the correlated replicas, then if you include correlated replicas, then it appears to mitigate it, but doesn't quite fix it. And then you end up doing a novel analytic continuation, the so-called Parisi ansatz, which gives you a monotonic free energy. So the main takeaway is that at least in some low-dimensional theories of gravity, there is at least one regime in which replica wormholes must make a large contribution to log Z to avoid various pathologies. And this contribution requires a non-trivial analytic continuation, which has some parallels to spin glasses. So this is the main takeaway, and now I'm going to go through some of the more computational details. So one thing we're going to need in JT Gravity is the calculation of the JT path integral over geometries that connect M boundaries with length beta. So this was computed by Saad Shankar Stanford. So this is the formula for it. this ZGM here, this is a function of the volume on moduli space of constant curvature spaces with M boundaries and genus G. And these are, there's a recursion relation that allows you to compute them, but not known analytically in M for arbitrary M. So here's an example. We have P comma 2 of beta. This is, we have the trumpet, and then we have the trumpet plus higher genus corrections and higher topologies. Now, the connected topologies are suppressed at large S naught, but you can do a pretty simple analysis that will show you that the connected topologies actually compete with the disconnected topologies, the disks, at beta to the 3/2 e to the minus S naught of order 1. So we're looking at non-perturbatively low temperatures here. Now, before I even go on, you might raise a concern, which is that you appear to need the main parameter in the problem, beta, to be non-perturbatively large in S naught, or the temperature to be non-perturbatively small. So in fact, you might actually raise two concerns. The first concern you could raise is that connected topologies can only dominate in a regime which requires something to be non-perturbative, some parameter to be non-perturbative. But this is really, I would argue, no different from the von Neumann entropy case, where the size of the Hilbert space of the radiation had to compete with e to the S naught. Now, another concern that you might raise is that the genus expansion is asymptotic at low temperatures, which is a valid concern. However, fortunately, it turns out that there's actually a separation of scales. There's an intermediate regime where the connected topologies dominate and the temperatures are not so low that the genus expansion is out of control. So we actually do have control over the genus expansion to the point where we can tell if the qualitative features we're seeing are valid or not if we include a resummation of the genus. And in fact, in a certain limit, the so-called Airy limit, we can actually sum the genus expansion exactly. And again, the qualitative features that we are seeing do not change. So hopefully, having addressed those two concerns, let me move on first to the calculation of the annealed free energy. So the annealed free energy is just computed by log of the gravitational path integral with a single boundary. And this is computed purely from the disconnected topologies, and it is non-monotonic in temperature. So I'll talk a little bit more in a moment about what all of these are, but roughly speaking, these are partial sums of the genus expansion, these blue curves here. And while they are, they don't look like they're doing anything that's well behaved in this region, they are getting better behaved in the region over here. Now, I'll say more about these blue curves and the red curve in the next slide, but the main point I wanted to make on this slide is that since the S is given by minus df dt, this means that we have some negative entropy somewhere, which is of course unphysical. So a few more words about the partial sums in this red curve here. So the non-monotonicity that we're seeing, that's this non-monotonicity over here, certainly is, it's within the regime of low temperature, but these partial sums here they look like they're pretty ill-behaved over here, but they're not ill-behaved over here. And so there is this intermediate temperature regime where we can actually expect that these partial sums are approximating correctly the behavior of this asymptotic series, is bounding it in the correct way. Now, another possibility is to actually work in the Airy limit. So that's this next slide here, which gives us this red curve. So in the Airy case, if S naught is large and TE to the 2S naught over 3 is fixed, then you can exchange the asymptotic genus expansion for an expansion in low temperature, and this you can sum exactly and get this red curve. So either way, the main takeaway from these slides about the genus expansion is that you shouldn't worry about it for what we're doing over here, because this non-monotonicity in the free energy is occurring at intermediate temperatures, and we don't expect that the genus expansion is poorly behaved or is going to fix it in any way. So that means that the annealed free energy really is very problematic. And we are therefore going to move to talk about the quenched free energy. Now, as I mentioned before, unfortunately, we can't actually compute this quantity as an analytic function of M because the ZGMs are only known recursively, so we can only compute them iteratively. So what we do instead is we define the truncated path integral, P little m big M, which connects up to capital M boundaries so in this iterative procedure here. So P12, 4 is going to have 12 boundaries and connect up to 4 of them. So you'll receive contributions where we have connections, so 4 are connected, all of them, or we have 2 pieces where 4 boundaries are connected and the rest have 3 boundaries connected, and so on. So this means that at any finite m, we can actually do the calculation and ask what is the annealed free energy for some finite m. In particular, the quenched free energy is going to be given by the limit as capital M goes to infinity. Now, for a given fixed m, we can analytically continue to m goes to 0, little m goes to 0, because we can actually compute this for a given value of capital M. And so here in this plot, we calculated the annealed free energy up to m equals 5. So it looks like the non-monotonicity in this region here is getting better. It looks like it might be getting mitigated as we go to progressively larger m. But it's not clear that it's going to save us as we take m to infinity. It might, but then again, it might not. Now, one thing to notice here is I can actually analytically continue to m goes to 0 in different ways. And this analytic continuation is not unique. So here are two different analytic continuations to m goes to 0. And they are qualitatively pretty similar, but quantitatively they're different. And so that's another complication that comes up here where we could say, well, finite or infinite m, the important thing is to get the analytic continuation right. And that might be what actually has to resolve the non-monotonicity problem. So we have learned that replica wormholes not only must contribute, since the annealed free energy is severely pathological, but they have to do so in a highly non-trivial way. There's some analytic continuation that without some top-down derivation, we're going to have to try and guess. And I mean, I find that, well, we were hoping we would be able to figure it out, but it seems that this is something that must be inherited potentially from quantum gravity, the correct analytic continuation. A question that you might ask is, what about Carlsons Theorem, which is something that is often used to guarantee the uniqueness of analytic continuation. So Carlsons Theorem, the way that the argument normally works is that you say, suppose I have two analytic continuations, and you essentially argue that the difference between them has to vanish. Now, unfortunately, our problem actually violates one of the assumptions of Carlsons Theorem. So it does not apply, and you can't use it to argue that there's some analytic continuation, which of course we've already seen because we know that we were able to construct multiple different analytic continuations of m goes to 0. There's also another version of this, I think, called Carlsons Theorem, which allows for super exponential growth. So the assumption that our system violates is the increase with m being sub-exponential or not super exponential. Now, Carlsons Theorem, I believe, actually allows for super exponential growth, but not too fast. And ours apparently also actually violates that as well. So it violates any theorem that would guarantee uniqueness of analytic continuation. And indeed, this is consistent with what we see, not analytic continuation actually not being unique. So I want to say a few words about the analogy with spin glasses. So I would say that finding the correct analytic continuation is very important for understanding the gravitational path integral better, because we would like to understand the generating functional and the free energy as computed by the gravitational path integral. And at least in this regime of JT, it looks like we actually need to have an analytic continuation that gives us a reasonable free energy. Without it, we just aren't able to compute the free energy from the gravitational path integral. So finding the correct analytic continuation, I would argue, is quite important. Now, I mentioned before that there's a similar phenomenon that occurs in spin glasses. So we might hope to learn something from that. So what happens in spin glasses? Well, there we have a situation where it's just quite similar. So the annealed free energy results in a negative entropy. And in fact, this curve here, this plot, you might think that this here is the area limit, and this here is the inclusion of replica wormholes, which still has some non-monotonicity. But in fact, this plot here is not of JT gravity at all, but actually is a plot of the Sherrington-Kirkpatrick Trick model of spin glasses. And this red curve, which looks so much like the area limit in JT gravity, is actually exactly the annealed free energy in Sherrington-Kirkpatrick spin glass model. And the blue curve is the inclusion of replica wormholes, or what they call correlated replicas, with this sort of naive analytic continuation. So again, this is non-monotonic. It's not as badly non-monotonic, but any non-monotonicity at all is very problematic. So the resolution in spin glasses is an analytic continuation that involves multi-step breaking of the SM replica symmetry. So replica symmetry breaking is very important in spin glasses to resolve this pathology. And we might hope to gain insight about what's happening in JT gravity from what is going on with the spin glasses. And I think I would be remiss not to comment on the fact that there have been some studies of low energy effective field theory of SYK that do discuss replica symmetry breaking. And I believe at least one step, although I'm not sure if they also discuss multi-step replica symmetry breaking. It's not immediately obvious what the connection is, but it certainly is intriguing. So with, I believe, 5 minutes left, let me go ahead and begin to finish up. So what have we done here? We were motivated by looking at the replica wormhole phenomenon in the gravitational path integral by looking at what I would argue is a more primitive quantity than the von Neumann entropy. And in fact, understanding this quantity better, log z, and how it's computed by the gravitational path integral is, I would say, very important for the von Neumann entropy simply because this appears in the von Neumann entropy. So if it's, as we've already seen, if you compute the von Neumann entropy of a pure state, you only get 0 if you also include this replica trick, this log z replica trick correctly. Otherwise, you could end up with subleading corrections for the von Neumann entropy of a pure state. So what we've looked specifically in JT Gravity. We also actually did a calculation in a very simplified model of CGHS Hat and found something that was pretty similar, which is that at sufficiently low temperatures, but not so low that the genus expansion is out of control, the free energy without replica wormholes is severely pathological. So again, we were able to control the genus expansion here. And in fact, in the Airy case, do a complete summation of the genus expansion and still see that you have this non-monotonicity in the free energy if all you include are just the disconnected boundaries, disconnected topologies. Now, of course, we haven't really argued very successfully that including replica wormholes can completely resolve the problem, simply because the non-monotonicity is still present with partial sum replica wormholes. So we didn't manage to get rid of the non-monotonicity altogether. Nonetheless, there are a couple of different places where we might imagine things come in to solve the problem and save the day, which is, for one, possibly the full sum over the replica wormholes really is monotonic with temperature. We weren't able to do the full sum. Or potentially there is some novel analytic continuation that removes the pathologies altogether. And if you buy the spin glass analogy, then the second possibility is is much more appealing and much more likely if you're subscribed to this analogy. And we might hope that by studying spin glasses a little bit better, perhaps we could see what kind of a novel analytic continuation is necessary. And or potentially we could imagine trying to derive it in some top-down fashion. So a few concrete things that we should be doing next. So figuring out the correct analytic continuation seems quite important. Now, I was harping on and on about the spin glass analogy, but I should be quite honest here, which is that the analogy is not quite sufficient, is not informative enough at the JT level. So in order to work with this analogy, you need to work in the saddle point approximation. And in pure JT, what we did, we worked with the full gravitational path integral. So if we really want to try to take something like the Parisi ansatz and make it work, then we would need to be working with a somewhat more complicated theory of gravity than pure JT. I should also mention some work in progress with Van Chandrasekaran, Sergio Quenched, and Sebastian Fischetti, which is a Lefkowitz-Maldacena style replica trick for a holographic calculation of the free energy in a saddle point approximation. We already have, we know how the Lefkowitz-Maldacena replica trick works for the von Neumann entropy and gives us the Ryuta-Yanagi formula. So then the question is there, what does it look like for the free energy replica trick? Now, there's a pretty significant complication here, which is that the m goes to 0 saddle is very hard to write down. Now, we're hoping that some progress can be made, for example, in the JT plus CFT, where you don't have to worry about back reaction on the metric. But this is all tentative and just really just a question at this point. Another question? Yeah.
Sorry, Daniel has a question?
Sure.
Sorry, I meant that I'll ask my question after the talk.
Oh, okay.
Yeah, I'm almost done. I realize I'm out of time at this point, but I have like one more slide left. So.
Okay.
So another question that we really should be asking is, in what regimes beyond non-perturbatively low temperature do replica wormholes dominate the free energy? So is there a regime where the compounded replica trick for the von Neumann entropy would actually give a different answer to leading order from the single replica trick that is used standard usage? In other words, is there a situation where we can actually see the impact of the replica trick for the free energy in the von Neumann entropy to leading order? So I think that's a very interesting question to ask and try to figure out. And more broadly, of course, where all of this is going is asking, what is the gravitational path integral really computing? And how do we unlock this black box? So thank you for your attention. And this is it for me.
All right. Well, thanks so much, Netta. And yeah, so we have some time for questions and discussion. Yeah, so we can start with you, Daniel.
Yeah, so at least in pure JT, there's this idea that it's at least in some sense equivalent to a matrix integral. Could that picture with the matrix integral somehow help figuring out what the analog of the Parisi ansatz is for doing the analytic continuation correctly?
Yeah, so certainly there's been some work in this direction. So for example, Clifford Johnson had some work on trying to, on computing the free energy in JT gravity from the perspective of the matrix integral. Now that work is in a very different regime of the very different temperature regime than what we work in. But my understanding is that it's much lower temperatures. It's more like things that go like e to the minus S naught rather than 2/3 S naught, which is a big difference. And in his work, I believe he doesn't actually see replica symmetry breaking. But it's also, it's a different regime. Now, I do think that technique overall, the very powerful techniques that Clifford uses, and more generally, understanding it in terms of the matrix integral, can actually be used to understand this better. Because when we compute the free energy in that context, we should certainly get something that's monotonic. We should be able to get a non-pathological free energy. And figuring out how to match that onto this gravitational calculation could potentially really help with understanding all of this. Yeah.
Okay, great. Oliver Jansen had a question.
Yes, hello. Thanks, Netta, for the really nice talk. I also had a question regarding the correct analytic continuation and also Carlsons theorem that you mentioned.
Yes.
So I believe that theorem tells you that if the nth moment grows less quickly than 2n factorial, then you can guarantee that the distribution on the partition function or on Z will be unique by moments.
Yeah.
But so in particular for that, you would need to know what the large n or infinite n behavior is.
Yes.
It seems like a really hard problem, at least so I was wondering, maybe in this area limit that you're looking at, that problem is doable, because if you're not in the area limit, then I think if you take the amount of boundaries to infinity, that's very much or closely related to taking the amount of boundaries finite, but taking to the genus to infinity. But there, the expansion that you wrote in genus is asymptotic. So you would need to sort of know, wouldn't you need to know something like what the non-perturbative completion? So you would need to know what exactly yeah. So basically the question is, how do you know what the asymptotics is as the amount of boundaries goes to infinity?
So I think, so I believe we do have some control of the understanding of the maximally connected topology as we go to infinity. So we do have some estimates on how this goes, to the point where I do believe that for Carlsons theorem, we actually can see that the fall off is going to be too big to apply it. Like it's going to grow too fast to apply it. So the question you ask about working in the area limit, whether we can actually do the calculation explicitly there, I'm not entirely sure what exactly you're asking with why the area limit makes a big difference here.
So yeah, so let's not consider the area limit. Just you wrote at
Sure.
some point a genus expansion for the gravitational path integral which connects to M boundaries. You wrote some asymptotic genus expansion, which is asymptotic at for any beta, right? So this means if you take the,
I believe that's right. Yes. Yes.
yeah. So so there the idea is if you take the coupling S naught, if you take it very large, then the first couple of terms in that genus expansion should be sufficient to approximate the right. So but now
Yes.
consider taking everything fixed, so S naught fixed, possibly large, but now taking the amount of boundaries to infinity. So there, I believe you can also explicitly show that the asymptotic series breaks down in a sense, in the following sense that the
Oh, I see what you're saying.
yeah, you just don't, well, in the usual genus expansion, you don't know what the well, at least without knowing what the non-perturbative completion is of the finite of the small n result.
Yes.
You won't even be able to estimate what the leading contribution is to the path integral that connects M boundaries. For this, yeah, because the asymptotic series expansion will break down. So the next term in the asymptotic series is gonna, or the first correction will start being larger than the leading term.
So for a given value of little m, you're saying that you don't have control, or you do?
No, for a given value of little m, it's always possible, I believe, to take the coupling S naught that you wrote. You can take that large enough so that the asymptotic series is under control, meaning that
Yes.
the
Okay.
first correction will be small compared to the leading one. That's true. But now consider just taking S naught fixed, and now taking the amount of boundaries to infinity. So so now the question is, what is the path integral that connects to M boundaries? And it's difficult to compute.
You're basically, are you just asking essentially whether we have enough control to determine whether Carlsons theorem is applicable or not?
Yeah, that's yes.
How
do you know what the behavior is at large amount of boundaries, basically?
So I think, let's see, you might be right that if we take everything into account, then we don't necessarily have the greatest control, but I think there is an analysis that we can do. Maybe this is why you were bringing up the area limit and some kind of a more formal analysis that we can do. I'll have to get back to you on that one, actually, now that I think about it. Yeah, let me get back to you on whether we can actually, especially in the area limit, whether this can work. Yeah, yeah.
That'd be a good thing to discuss in the discussion session or another.
Yeah, definitely.
Thanks a lot.
All right, great. Mukund Rangamani.
Hi, Netta.
Mukund.
I have a mildly semantic question. It's something that really confuses me with your terminology.
Yeah.
I don't think of gravitational path integrals as computing entropy. They never compute entropy. They only compute free energies. This is what Gibbons and Hawking computed. And what you compute from there is use thermodynamics to get the entropy. It's true that when you compute the von Neumann entropy, you get the entropy on the nose because the n=1 limit involves taking effectively a temperature derivative.
Sure.
So I understand the difference between Quenched and Anneal, but I was wondering whether you had any more than that in your discussion, because I think of all the replica path integrals one does in gravity as actually replica path integrals for free energy.
Sorry, could you just repeat that last word?
For free energy, not for entropy.
So I'm not actually, so let me start. I'm just going to scroll up here. I'm not really, I think maybe I'm missing something semantic here, but I'm just going to go up to the replica trick for a second. So we use there it is. So we use the replica trick here we use the gravitational path integral via the replica trick to compute a free energy, which I think is consistent with what you say. We're computing a free energy using the gravitational replica trick, the gravitational path integral. I agree with you that the gravitational path integral a priori, if you want to use it to compute an entropy, you really have to first compute a free energy. And then you work in, you can work in some thermal black hole equilibrium, and of course it's Euclidean, so that's what you're doing, and then you can use that, which of course is essentially what you could interpret that as what I'm saying over here, which is that really you first need to worry about how the gravitational path integral is computing the free energy before you can worry about how to obtain an entropy out of that. So I think I agree with what you're saying. And I think we do need to think about the free energy from the gravitational path integral first before we think about the entropy.
Okay, thanks.
Okay, great. Mark van Ramsden?
Hi, Netta. So I was just wondering if there's any in principle calculation that doesn't use the replica trick that you could like compare with if you, and when sometimes computing entanglement entropies, there are alternatives, but is it possible here?
So I think I personally do not know of another way to compute the quenched free energy other than using the replica trick, unless you knew essentially what kind of average you wanted to do, if you knew the kind of ensemble and what kind of measure you had. So this is a little bit related to Daniel's earlier question, which is, can you essentially use the, can you use the fact that JT gravity is understood in a different context, not just as a gravitational theory, but in terms of the matrix integral? Can you use that in order to understand better how to compute this log z? So if you know what your average constituents are, then I think you could. But without knowing that, I think the replica trick is kind of your only hope.
Okay, great. Thanks. Any other questions? Or just anyone who wants to jump in and discuss?
Well, I think Greg Moore is asking an interesting question if he wants to speak up.
Oh, okay, yeah.
They're in the chat.
Greg Moore, please.
Hi, I'm far from an expert on this, but you know, how supposing you were talking about finding the right analytic continuation. I don't understand the definition of right.
Ah, great. Yes. So I could be a cynic and tell you the right analytic continuation is one that gives us the answer we want, but I'm going to refrain from taking that particular perspective.
Surely you have some list. You have some list
Yes,
of basic physical principles, like you used monotonicity of the U.
That's right.
So you must have some list, and that list does not determine the analytic continuation uniquely. And so, in principle, I don't know if that's true, but let's suppose that you write a list of physical desiderata. That list does not determine the answer uniquely. So then, in principle, you might have two different analytic continuations, both of which satisfy your list of desiderata, but lead to different sensible results.
I agree with that completely. I think that there probably is a single correct analytic continuation that gives us the answer if we knew if we would subscribe to the ensemble interpretation, just for ease of notation right now, if we knew exactly what kind of ensemble averaging we had top down from quantum gravity, we knew what the measure is, we knew everything, then there would be a unique answer for the free energy. And whatever analytic continuation reproduces that is, of course, the correct one. Now, I think the question you're asking is very interesting in the sense of in the low energy limit, where we don't have access to non-perturbative quantum gravity, and we're trying to figure out what is the correct analytic continuation. If we have two, then how do we figure out which one of these is most likely to have come from a top-down construction from quantum gravity, and which one of these is in some sense a red herring? And to be honest, sorry, what was that?
Well, maybe different matrix models give different analytic continuations that are they're all sensible, right? I don't know.
Actually, I think there's a very interesting parallel here with the so-called C equals 1 S matrix. So you couple 2D gravity to a massless scalar field, periodic scalar field. And, that was studied in the old 90s matrix model days. And there are several, there's not a unique non-perturbatively defined S matrix. I guess there are a few points. One is also that at large energies, this asymptotic genus expansion just breaks down, which is similar to a question that was asked earlier. So that happens. But then more importantly for this, there are many different ways of giving a sensible physical non-perturbative completion. Now, I guess people do prefer one these days, which is the type 2 strength. But I think that's an interesting example to keep in mind.
Yes, I agree. And I think if there are multiple non-perturbative completions that have different analytic continuation, that result in different analytic continuations in this replica trick, then I mean that would be extremely interesting. What distinguishes between these replica tricks between the analytic continuations from these two different types of models, that both of which have the same what looks like a low energy limit. So I agree that I think at the end of the day, when I say the right analytic continuation, you're right that there could be more than one depending on how we choose to non-perturbatively complete the system. I agree.
Okay. So Emil Martinek in the chat says a naive question: why is thermodynamics supposed to apply at these extremely low temperatures? Are these results suggesting that there's some sort of phase transition?
Well, I guess I would be a little bit careful with the use of phase transition, because that normally assumes we're working in some kind of a saddle point approximation, an exchange of saddles, exchange of dominance in the saddles, whereas here we're working with the full gravitational path integral. You could complain, you could say everything breaks down at these extremely low temperatures, but I would argue that we're not working with temperatures of order e to the minus s naught, rather e to the minus 2 s naught over 3. And given that the genus expansion is under control in that regime, given that the partial sums appear to be well behaved and giving us a good bound, then I would say that I would not say we're strictly speaking working in this regime of non-perturbative, where non-perturbative effects are truly modifying the basic expectation of the gravitational thermodynamics.
Okay, thanks. Juan, you had a question?
The ambiguity in the analytic continuation in M, was it a feature of the fixed capital M limit, or is it, do you expect it to be true even if we don't have that, if we are not computing that?
So we were only able to establish it at fixed capital M. So which is one of the reasons I said that it's possible things are completely fine when we take the capital M goes to infinity limit, and we just don't know. So it is possible that the analytic continuation is not a problem if you actually end up being able to take the full limit as capital M goes to infinity. So that is certainly a possibility.
Henry, you had your hand raised?
Yeah, it's just thanks for the nice talk, Netta. Just one comment on perhaps some of the things that Greg was asking and so forth. My understanding from some of Clifford Johnson's recent work is that he's been studying different classes of matrix models that have precisely the same genus expansion, but a different non-perturbative completion in terms of integral. There are different classes of matrices, and these I think would give different answers for the free energies in the limit you're studying. And perhaps one other small comment while I'm here is that, so you mentioned the CGHS Hat Model. I think there are two ways in which the analytic continuation could be ambiguous. So one of them is whether just the partition function is, or sort of the probability distribution for Z is ambiguous. But another way is if actually the log is ambiguous. So in this CGHS Hat Model, for example, I think you know what the probability distribution is. It has to be a Gaussian.
That's
but
right.
Because that has support on negative values of the partition function, which is obviously pathological, it means that there's ambiguity in how to define the log. And I think that is, so there's possibly two different ambiguities that could show up. One of them is a sign of a pathology, and one of them is just a sign that you don't know what the non-perturbative completion is.
That's right. I'm a little bit hesitant to draw conclusions from the CGHS Hat model because it's I mean, it's very simple and in some sense pathological. But you're right that it does point to the possibility of there being multiple sources for this ambiguity.
Okay, thanks. Any other questions? Anyone else?
What is the CGHS hat model?
So it's a simplification of CGHS, which essentially just the important point for this replica trick calculation is that it essentially receives contributions only from two topologies, just the two boundaries being connected and versus one boundary. So disconnected boundaries versus two connected boundaries, which makes it, I mean, asymptotically flat, and it makes it very simple to work with. But one does have to wonder about how physical it actually is.
Okay, thank you.
Okay, anyone else? All right. Alex?
Yeah, hi Netta, thanks for the nice talk. Quick question, could you comment on the differences between JT and then D greater or equal to 2? Is it clear that there's any pathology in higher dimensions that you need to cure?
No, so I don't know at all what happens in higher dimensions. This calculation was made possible by the analysis of Shankar Stanford, but I think it would certainly be interesting to investigate in higher dimensions, but I think we just don't have the tools that we need in order to, I mean, basically we needed here the gravitational path integral and all of the beautiful calculations of SSS. So do we necessarily need to, well, okay, so there are two questions here that I think may be relevant for you, for what you're asking, which is, the first of which is this replica trick for the free energy, is there any chance that it would actually be relevant for higher dimensions? And the second is there any chance that it being relevant means that at low temperatures we have this non-monotonicity problem? Because just the non-monotonicity is not the only way in which we might be forced to include the connected topologies into the free energy. We may not. There may be other ways in which we have to do this. But the short answer to your question is I don't know what happens in higher dimensions, and I don't know that this would happen there. And of course, you could say, JT Gravity is very special, and we think that it's described by some kind of an average, and maybe higher dimensions are not. And so you could ask, do we really expect the same thing to happen there? The short answer again is I don't know. If we expect that the replica wormholes can contribute to the von Neumann entropy in higher dimensions, which we probably do because we hope that the quantum extremal surface formula for the evaporating black hole is valid and can be justified there too, then we should be asking whether replica wormholes can contribute to the free energy replica trick also. But what the answer is, I don't know.
So if there was a problem, it would have to be that, I guess, the free energy of the the quantum fields on top of thermal ADS that goes like T to some power. But you're saying when T is exponentially small, maybe there's non-perturbative corrections that change, that give you a negative entropy, and so there's a problem to fix. Would that be the idea?
Possibly. What you really want, you want some parameter in the problem, and in JT we basically only have the temperature, but you want some parameter in the problem to be non-perturbative so that you can actually have the connected topologies play a major role. And again, I don't know, I don't want to commit to there being pathologies in higher dimensions, because for all we know, they could be quite different from what happens in 2D.
I see. Thanks.
Okay, maybe one last question. Anyone has one? All right, well, if not, then thank you, Netta, again.